Good afternoon, everybody. Welcome to another seminar. We have today with us Professor Richard Tilley, who's going to give us a very interesting seminar on liquid phase synthesis of nanocrystals. Richard has fairly recently joined UNSW. He's the director of the EMU in February, was it? February, March?
April.
April.
Yes.
Okay, so 3 or 4 months now. And so that's a very interesting position for him to be involved with. He was previously at Victoria University in Wellington, where he headed up the part of the McDermott Institute there in Victoria. Prior to that, he did his a master's degree in Oxford University, and then went on to do his PhD at Cambridge University in the UK, and then he did a postdoctoral fellowship at in Toshiba in their R&D centre in Japan, before moving to Victoria University.
Right.
So we're very glad to have Richard giving us this presentation. It's an area, of course, that we've got a lot of interest in some of our activities here in our school. So I think we'll be very interested to hear what Richard had to say. So thanks very much, Richard.
Cheers, Gavin. Yeah, so I've been here, I think, for probably about 11 weeks now. So as Gavin said, I'm the new director for the Electron microscope unit. And I thought it'd be good to come to the school and kind of show myself, show my face and introduce myself, but also to talk a little bit about the research we do synthesizing and making nanoparticles. So my background is that I'm a chemist as well as an electron microscopist, and we do a lot of work and research over the years synthesizing nanocrystals in solution. So in terms of the research that we do, we do make quite a variety of particles, as you can see. So we've done a lot of work making magnetic particles. We've done a lot of work making metal particles, and I'll briefly touch on both of those topics. The other work that we've done quite a lot of work on over the years is basically making quantum dots as well. So in terms of what we do in the group, we do try and specialize and focus on the solution synthesis, that's our expertise, and also the electron microscopy characterization. Once we've made the materials, we really like ideally to find collaborators, and we do collaborate very widely. So one of the main reasons I'm here today is to hopefully find some good collaborators to use our materials. In terms of how we synthesize the nanoparticles, there's a couple of different methods that we use, and I'll talk a lot about how we make the silicon dots and the germanium dots, which is again by a slightly different route, but the most common way that most people make nanocrystals, and we do as well, is by decomposition reactions. So say for example you want to make some iron particles. What you'd typically do is take an iron organometallic precursor, so your iron precursor, you'd heat it up, decompose your precursor, and then you'd end up with iron particles. So there's a couple of different ways that this is typically done. One way that we do a lot of experiments with, particularly to make metal particles, is using something called a Fischer-Porter bottle. So that's this bottle here. So in the bottle, we essentially just fill it with an atmosphere of hydrogen gas, and that hydrogen gas helps the precursor decompose. So you can see the little reddy orange solution in the bottle there. That'll be the solution of the precursor. So we fill this bottle with hydrogen gas, we put it in an oven, and then we kind of leave it cooking. And it's kind of quite a nice way. There's only 2 or 3 groups in the world that really use this way to make nanoparticles, these bottles. So we do tend to make things which are a little bit unique or a little bit different to other people. So when we're doing this cooking in these bottles, typically the reaction can take about one hour to about 3 days to make what we're after. So it's a very, very slow kind of cooking process compared to, say, a hot injection method, which is also something we do but is more commonly used for synthesizing nanoparticles, where you have a hot solution and you inject your precursor in, and then your reaction is pretty much instantaneous. You know, it can be over in the factor of a few seconds sometimes. When we do our reactions, like all chemists for these synthesis protocols, we always put in some surfactant, and it's our surfactant that's really trying to control the size and the shape of the nanoparticles that we make. Okay, so I'll talk mainly about the work that we've been doing making some quantum dots. and some optical materials. So the work we've been doing on silicon germanium quantum dots, we've been doing this research really for a number of years, and we've probably been doing this research now for about 10 years in terms of the synthesis of the silicon dots. So I'm sure you're all familiar with kind of why the interest in quantum dots, but you know, things like sharper emission and purer colors from the emission, and also particularly the stability compared to organic dyes. A lot of the research that we've focused on have been predominantly for biological applications, so particularly looking at the emission properties of the dots and trying to use the emission. So our first kind of interest in the silicon work really started, as I said, about 10 years ago, in about 2005. And really, I guess our interest stemmed from, at the time, this was, you know, just when there was all this interest beginning with all these cadmium selenide-based quantum dots and nanoparticles. And when all the cadmium-based nanoparticles were first made by the first groups, they essentially were turning around and telling everybody that they weren't toxic and they didn't have any toxicity at all. And there was a nice paper in 2004 by Durfus, who was essentially a medical researcher, and he turned around and said, well, of course you haven't shown that they're toxic, because all of the cell lines that you've been testing the toxicity in were essentially not susceptible to heavy metal poisoning. So he then did toxicity studies in liver cell lines, which are susceptible to heavy metal poisoning, and showed, of course, that the cadmium-based dots were highly toxic. So after that, we were really interested, I guess, in trying to make some quantum dots and materials which really shouldn't be toxic. So the silicon dots that we first made, so this is a picture of this, some emission from the silicon dots we made. So they do have the low toxicity, as I said. And essentially, this was in collaboration with Professor Kenji Yamamoto at the International Medical Center of Japan. So all of the blue color that you can see from the cells, all of that blue color comes from the light emission that we're getting from our silicon dots. So the method that we developed to make the dots, and this has been quite a successful method and quite widely used by a number of people now around the world, is really quite a simple method. So this is a mice cell synthesis. So essentially we started off when we were first doing the synthesis. Now we've moved to using things like iron bottom flasks just to make the synthesis a bit easier. But essentially the synthesis that we started off doing, we were doing it in a glove box, and we just had a beaker, and then in our beaker we would use some silicon tetrachloride, or if we're making germanium dots, we'd use some germanium tetrachloride. And then we'd just put in some reducing agents, so say for example some lithium aluminium hydride. And your lithium aluminium hydride will reduce your silicon down, silicon 4 from the chloride down to silicon, and you can make some nice silicon dots. The important thing with the synthesis is that you need to do it in an inert atmosphere, so obviously silicon is going to be sensitive to oxygen and water, so you do need to do it in an inert atmosphere. And another important point was putting in a surfactant, so we were using a surfactant called TOAB, and it seemed to be important to use the surfactant in terms of actually sticking to the silicon before it was reacting and forming the silicon dots, because if you do this reaction, if you add silicon tetrachloride with lithium aluminium hydride, you can form silane. So it seemed that the role of the surfactant was important in terms of really kind of limiting the silane formation. But you do have to be a little bit careful doing this reaction. So once we've made the dots, we did quite a bit of research then looking at different capping protocols and how to really protect the surface and passivate the surface of the silicon particles once they're made. So once we've done our reaction, we started off with, say, our silicon precursor. Once we've done our reaction, we make some silicon dots, and essentially they have hydrogen termination on the surface. And we can react that silicon-hydrogen bond with a carbon double bond. So it's just a carbon double bond that we're reacting with. And you can react that carbon double bond with your silicon hydrogen bond, essentially to end up with a robust silicon carbon bond on the surface of your dots. So the good thing about that silicon carbon bond is essentially it is a covalent bond, so it is a robust bond. So if we do the passivation properly, and we do a proper passivation reaction, a proper coating reaction, essentially the dots that we make do tend to then be stable to further oxidation or any oxidation if we do get the passivation correct. And in the beginning of kind of the process, when we first started doing these reactions, we were tending to react and catalyze that silicon carbon bond formation with a platinum catalyst. But essentially these days we use just UV light excitation to passivate the surface of the dots and get that reaction going. And that's a far more effective way. So once we'd made these kind of darling lovely silicon dots, of course we wanted to do the kind of the bioimaging, which we could do quite successfully. The other side that we wanted to really show, of course, was the low toxicity. It's no good making dots of, say, silicon and then them being highly toxic. So when we were first doing some toxicity studies at the beginning, we essentially did find that they were highly toxic, and we were getting quite a lot of toxicity from the dots. And the big problem was not the dots themselves, but essentially whenever you're doing any of these solution phase reactions, you do have kind of surfactants around and you do have byproducts. So say, for example, if you're doing this reaction with the silicon tetrachloride lithium aluminium hydride, then you can end up making a lot of lithium chloride as one of the products. So it's all these kind of byproducts that are essentially were essentially causing the toxicity for us. So we did spend quite a bit of time really developing protocols and looking at protocols for purifying the dots and really cleaning the dots. So the most successful method that we really found and really made was using column chromatography. So if you're familiar with a chemistry lab, and particularly say the organometallic chemists or the organic chemists, they use these long columns which they put their chemicals down to essentially do the column chromatography and separate out the impurities. So we developed quite a few methods in terms of putting our silicon dots down different columns to remove all the impurities. And we've done this kind of more quantitative, I guess, looking at the organic molecules present, but this is just, say, from the electron microscopy. So hopefully you can see that before we put our dots down the column, there's lots of kind of junky stuff in the background on the TEM image, and then afterwards you've got kind of quite nice, quite clean dots. And in terms of the dots that we make, we typically make silicon dots which we can tune or control the size, but typically the dots we make are, say, about 1.5 nanometers, maybe 2 nanometers in size. Those are typically the ones we look at making. And the bore radius of silicon is about 4 nanometers, so you do need to be down around that size in terms of seeing something a little bit different. So this is just showing that we've done some further work in terms of the silicon surfaces. So this was quite a nice study just showing that we can get different surface different surface cappings on our particles. So I guess the idea behind this was typically if you have a nanoparticle or a quantum dot and you want to have a different functional group on the surface, normally you would just say, okay, I want an alcohol group, so I'll bind a molecule with an alcohol group onto our particles. Or if you want an acid group, you bind a molecule with an acid group. But a colleague of mine suggested, Pete Northcote, an organic chemist, said, well, why don't you just react one molecule on the surface, and then you have a reactive group on the end that's your kind of handle, and you can change your functionality by reacting that carbon double bond at the end of the molecule attached to the surface of your dot. So this is what we did. So we did a few different reactions to give different surface functionalities on our dots. So for example, we could oxidize up that double bond to give some epoxide, and we could further react that, for example, to make alcohol functionalized quantum dots. So I guess there's always, again, the question of toxicity for these materials, and it's always a kind of ever-present question, the toxicity of nanomaterials. So again, this was kind of quite an interesting platform to have a look at toxicity in terms of having different capping molecules and different surface functionalizations on particles. And essentially what we found was what you would expect, that if you have a highly reactive epoxide group on the surface of your dots, that's a highly reactive group, and essentially the dots we found did have some toxicity. But if you have a benign group, such as an alcohol group on the surface of your dots, then essentially you have a low toxicity. In terms of the optical properties, I guess this has always been where we've kind of had lots of challenges with the silicon dots. In terms of actually kind of changing or tuning the optical properties, it's essentially exceptionally difficult. As I'll show you, we've tried a few different avenues, and other people in the literature have also tried a few different avenues to tune the optical properties, but essentially it's really, really tough. So this is kind of the absorption properties we get for the silicon dots. So we get some absorption around 300, 350, and then we're getting our emission at about 450 nanometers. So we're typically getting a blue color out of the particles. And the quantum yields that we typically get are around 10%. And in terms of the literature, that seems to be a value which is, I guess, quite trustworthy. Some people report higher values, but yeah, certainly what most groups seem to report is quantum yields of, say, about 10, 15%. So we've always been interested, and there's always been quite I guess, a lot of discussion around the literature on the origins of the luminescence of silicon nanoparticles. And in terms of the origins of the luminescence, then I guess really what we've always felt is it probably comes from some impurities in the system, or some kind of dopants in the system. I guess for silicon you obviously wouldn't expect it to emit, and even though we were making these very small particles and we were getting light out and other people were getting light out, there was always a good question of where the origin of the luminescence was actually coming from. So we did a nice study with John Vino and Susan Kaslerich. So they're two of the other pioneers for the solution phase synthesis of silicon dots. So essentially what John did, and he's in Alberta and Susan's at UC Davis, essentially what we did was John took all our dots made from the 3 different groups and essentially try and find out if the emission properties and the optical properties were the same. And this stemmed from something he noticed in his lab, where he made some of his silicon dots which were glowing this nice red color, and that's typically associated if you have silicon dots which have a silicon-oxygen bond on the surface. And he was playing around and he put in a capping molecule which had a nitrogen group on the surface, and then essentially he found that his dots turned to a blue-emitting dot. So his hypothesis was essentially that if you're getting out a blue color, it's probably coming from some silicon-nitrogen entity in the dot or on the surface of the dot, and that was kind of the transition he saw. So we had a good look at our dots and compared them to his dots, and that seems to be about the best bet in terms of thinking about where the emission comes from. So probably it's coming from a silicon-nitrogen bond or entity on the surface of the dots. And this is more recent work that we've just published a couple of months ago. So this is Ben McVeigh's work. And essentially, again, we were trying to see if we could tune some of the emission from the dots. So this time we were trying to put in some different metals. So this is trying to tune the emission from the dots or the optical properties by putting in some transition metals. So we put in some manganese, some nickel, some copper. Again, it was quite easy to do. So you take your, say, your silicon tetrachloride, you can just put in some metal chloride and do your reduction, and then you'll dope your dots. And as I said, then we take our silicon hydrogen bond and react it with a carbon double bond to passivate the surface. And essentially what we found was that we could shift the emission a little bit. So if we put in these different transition metals, the manganese, the nickel and the copper, we could shift the emission by about 50 nanometers, which I guess is useful, but maybe of limited use for, in terms of, say, biological applications, you're always looking for dots that maybe will be emitting in the red region or the yellow region, which is the region which is best for kind of the transparency through the skin. So really, we're always trying to shift, or have been trying to shift, the emission from our dots away from the blue for those biological applications down really towards the red. So although we could shift a little bit from blue to kind of a bluey green, it wasn't really as far as we wanted to shift. But it was quite an interesting process for all of that. And in terms of the stability, we found that if the quantum dots were copper doped, they seemed to be the most stable. Certainly with some of the other metals, the manganese and the nickel, the shift in the luminescence would revert back over time. So that's, I guess, where we're at to with silicon dots. So we tried to, as I said, kind of play around with them with different dopings. We've also done work with germanium as well. So this is just an example with germanium. So this is just showing with some TM that you can tune or control the size of the dots. And we've done the same with silicon as well. So this is just quite a simple method. If we just change our reducing agent, we can change the size of our dots. So if we use a reducing agent which is very strong, gives you a very rapid reaction. You put in your reducing agent, you react all your silicon or germanium, you gobble up all that precursor, and then you ended up with very small particles, very small dots. But if you use a very weak reducing agent, such as, say, sodium borohydride, then the reaction's a lot slower and you end up having time to grow these bigger particles. And again, in terms of the optical properties of the germanium, they turn out to be very similar to the silicon dots in terms of the emission and the absorption as well. So you're still looking at kind of emission around this kind of 450, 500 regime. It was a bit hard to say whether we're seeing any size selective shift in the emission. Possibly, possibly not. So yeah, that's where we got to with the germanium. So I think we're going to have a go at probably putting some different dopants into the germanium and seeing what happens in the germanium system. So I guess that's kind of a bit of a tour of the work we've done on the silicon and the germanium systems. I guess in terms of where they're at the moment, certainly in terms of the emission, I still think that although there are reports from around the world of higher quantum yields, I still think that there are limits in terms of kind of the quantum yields you can get out of them. The big advantage is, of course, the low toxicity. This is some example from the literature just showing, and this is some recent work from John Vino's group, this is just showing that if he has his silicon dots and he does passivate them with different capping molecules, with different functional groups, he is getting out different colours. And there have been reports in the literature of kind of getting out different colours from silicon dots if you do change the surface functionalizations. But the issue with all of these pretty colours that he's getting, and he admitted this to me, is basically they don't hang around for very long. So none of these kind of colours or emissions are very stable at all. So we could take a nice kind of snapshot of them, and that was about it for pretty much most of them. So the colours that people can reliably get out and strongly get out are essentially this kind of reddy colour and also the blue colour that we get. They seem to be the two colours that people can get out and be the most stable over time. Okay, so that's silicon and germanium. I'll just briefly mention some of the work we've been doing on sulfides. So we did some work a few years ago on tin sulfide. So this was a method using this surfactant here, or surfactants based on this to make some different tin sulfide dots. So essentially you've got three. We did some different reactions looking at having 3 alcohol groups on this molecule, or 2 alcohol groups, or 1 alcohol group. So just playing around with this molecule. And essentially we were looking at seeing if we could tune or change the size of the tin sulfide dots that we were making. And that's essentially what we could do. So if we had 3 alcohol groups on our surfactant, the 3 alcohol groups would bind strongly to the particle as it was nucleating and growing. So we'd kind of control the size and keep the size of the dots very small. So we're typically making, say, about 3 or 4 nanometers. If we have 2 alcohol groups, there wasn't quite as strong binding, so your dots weren't quite as small. And then if we only had 1 alcohol group, then they were growing to a larger size. So we looked at the optical properties, and we did seem to see some shift in terms of the optical properties compared to what you would expect from the bulk material. So we did suggest that we were seeing some quantum confinement effects in terms of where we were kind of seeing our band gap. So our band gap that we were observing for the smaller dots was about 1.1 eV. And I guess for us this was kind of a little bit of a point as well in terms of what we could achieve and in terms of the way we were doing things. So this was still at a time when you could get a paper in JAX by synthesizing some dots and looking at the optical properties. So we didn't do any device fabrication, and we didn't do making any devices from these kind of materials. And that was mainly from our side due to not having some good local collaborators around in New Zealand that we could work with to make some devices. So in 2009 you could still get kind of reasonable level papers just looking at the synthesis and the optical properties, but of course everything's changed now. So you do need to have those devices, as you guys know, on papers to get them into the higher impact factor journals. So we've done so that was with the tin sulfide, and now the recent work we've been doing is looking at some CZTS quantum dots. So again, these are, as I'm sure a lot of people here know, lots of people are suggesting they should be very good quantum dot materials in terms of solar cells. So obviously, earth-abundant elements and earth-abundant materials. There have been some nice papers in terms of syntheses of making the CZTS dots. So we've been having a bit of a dabble and a bit of a go ourselves. So the way we've been doing it is essentially taking some metal precursors and using some amine surfactants to stick to the surface of our dots, and we've been making some dots that way. I guess when we first started out with the experiments and the reactions, it was pretty hard to control the size of the dots and also the composition. So what we've been doing is essentially looking at some seeded growth and putting in some different seeds. So if we do that and we tune all the reaction variables, we're starting to make some pretty reasonable dots. So the dots are of a reasonable monodispersity, and also the XRD is showing that we're making the correct phase as well. So I guess the next step we want to do is really look at tuning the variables, so see if we can get some tuning of the composition, and also we need to really do some proper optical studies and hopefully some device fabrication as well. This is just some EDS mapping showing that we got all of the 4 elements in the dots, so you really need to prove that you've made your CZTS dots. So this is just showing that we got all of our different elements present, as we should do. So I guess these are materials that it would be great to find some collaborators for. Okay, so we've done some preliminary optical characterization. So the band gap for these is about 1.45 EV. But as I said, I guess what we're really going to be trying to do next is really putting in some different elements and seeing if we can get some variety there as well. Okay, so I think that's kind of the stuff I was going to say on the quantum dots. I'll just quickly breeze through some other pretty pictures, as essentially with the work we do and having the electron microscope as your primary characterization technique, you always end up making some pretty pictures as your kind of outputs, which was also nice. So I'll just quickly show you some of the other materials that we make, just in case there is any interest. So this is some work we've done making some magnetic particles. So the particles we focused on for the magnetic particles actually have an iron metal core and an iron oxide shell. So with these particles, once we've made them, they do oxidize a little bit, so you have a thin iron oxide shell and an iron metal core. And essentially what we were looking at with these materials is that you can really have a lot of biological applications for magnetic nanoparticles. So particularly, say, for the iron oxide particles, they can be used for MRI contrast agents. But the problem is with iron oxide, essentially it's a very weakly magnetic material. You're only talking about rust particles, essentially. So we did want to see if we could use particles which have an iron core, so they should have really stronger magnetic properties compared to the iron oxides. So, and that's essentially what we showed. So they do have stronger magnetic properties, so you then do have better contrast for the MRI. So you always need a little bit of the eye of the believer, don't you, with these kind of things. So this is showing some MRI contrast in terms of the spleen. So the contrast agents for the magnetic particles were essentially making the part that you're looking at, essentially making it darker. So hopefully you can see that if you don't have any contrast agent, it's quite white. If you put in some iron oxide contrast agents, it's a bit grayer. And if we put in our iron-based contrast agents, then it's darker still. So essentially with the iron contrast agents we had, we developed, they basically gave twice the contrast in terms of compared to iron oxide particles. So that's work that we're looking to hopefully take further as well, in terms of really looking at these hyperthermia applications where you can use the particle to not only act as a contrast agent, but if you heat them in a magnetic field, actually heat up the cells in the tumour and actually cure and kill the tumour as well. And then this is a series of really, I guess, pretty pictures in terms of some different metals we've also made. So we had some fun making some nickel cubes. So these are nickel metal. So as you can see, they're all very nicely monodispersed and nicely arranged. We made some nickel branch structures as well. We made some palladium branch structures. So this is some palladium structures that, again, we could really follow and make some different structures and shapes with different growth mechanisms. And this is with platinum. So again, with platinum, just watching how we can turn, say, from this shaped particle and following all the growth mechanisms of how we end up with different shapes again. So that was nickel, palladium, platinum. We've also looked at more different structures as well. So this is ruthenium, which has a hexagonal close packed structure compared to the other metals, which have a face-centered cubic structure. So whenever we do all these kind of syntheses and we make quite a variety of different shapes of particles, we're still quite often asked whether it's possible really to be predictive in terms of guessing or predicting what shape you will make in terms of the particles. So I still think it's really exceptionally difficult to be too predictive. Certainly if you want to make a nickel cube, well, it's got a cubic crystal structure, so you would expect, I guess, to make a cubic shape. But this is with ruthenium, and essentially when we had one type of surfactant, we made this kind of shapes. But then if we put in a very similar surfactant, so a similar amine surfactant, we suddenly made these hourglass shapes, which really have kind of quite nice definition and control. But to do a chemical reaction and predict that you're going to make an hourglass-shaped particle at the end of it, I think is really still very difficult. And this is some high-resolution transmission electron microscopy. So we can always go backwards and explain how we managed to make the shape. So essentially we have some high-resolution electron microscopy, and we can see all the surface atoms, and then essentially work out what surface facets you have on the particles. And it's what surface facets you have that essentially control the shape. In terms of the current work that we're doing on the metal systems, we've done, like most people, a lot of work on single metal systems, and now we're looking at bimetallic systems. So this is, for example, some particles which are bimetallic. So these are particles which have a gold core and a palladium shell. So at the center of a particle we have a gold core, and then on the surface we've coated palladium. So this is some EDX mapping. So you can nicely pick out with the EDX mapping. So this is on an aberration corrected TM. So you can nicely pick out your gold core, and then with the EDX mapping you can pick out your palladium shell. And this is the high angle annular dart field. And this essentially shows you different contrast in terms of having different elements present. So if you have a heavy metal, a heavy element, that's going to show up bright. So again, you can pick out your gold core with the high angle annular dart field, and then you have a lighter shell from your contrast from your palladium shell. So this is some kind of illustration of some nice electron microscopy you can do to characterize these materials. So we're looking at those in terms of catalytic applications. So I think those are probably where we're about at. So the latest ones we've been making are trying to get to even more and more exotic shapes. So this is kind of the latest ones that we've been brewing up. So these ones, again, are bimetallic. So now we're using systems where you have two metals. We're starting to try and control and make some branch shapes. So the idea, I guess, is that we can maybe one day be able to grow three-dimensional structures from a bottom-up approach. So we're just kind of beginning at the start of it all. But essentially, these ones, we have a palladium core, and then we're growing little kind of ruthenium arms off the palladium core. And again, this is some nice EDX mapping to show that we have this is a gold core in this example, but a gold core and then some ruthenium arms growing off. Okay. So I guess that's kind of mainly it. This is a picture of my team from my old university. As universities sometimes do, they like to try and get their propaganda machines going, don't they? So they decided to take this artistic picture of the team. I do wonder if it's a metaphor, though, that all my group are looking in a different direction to the direction I'm looking at, but there we go. So in terms of the people that have done a lot of this work, a lot of the silicon and germanium work have been done by previous students, but Ben is the student that's come across from New Zealand, so he's been going to be doing a lot of the quantum dot synthesis here and getting it going. And Ben is sitting over there, aren't you, Ben? Trying to sink into the ground. And so Lucy has also come across, and she's the one who's making those kind of very pretty branch structures that I showed at the end. Okay, so I guess the only other thing to say is obviously I'm the new director of the EM unit. I know that this school is a huge user of the EM unit. So yeah, if anyone has any questions about the EMU, then I'm the person to come and ask and speak to about it. So certainly it's got some good facilities at the moment. I think we need to kind of think collectively about what instrumentation we need in the future. Certainly the transmission electron microscope side, the TEM side, does need some kind of attention and some new kit. So a LEAF grant was put in this year for a new TEM with the support of this school. So we do need, I think, on the TEM side particularly to kind of take things forward. But we do have these fantastic new rooms just built in the new kind of materials building. So there's a lot of opportunity there. Okay, thank you very much.
Thank you very much, Richard. Very interesting talk, and I'm sure we'll take some questions.
Yeah, sure.
Could you please go to the slide with the doping where you have manganese and nickel, I think, and silicon? Yeah, that one. When you talk about doping, do you mean that actually in a chemical sense, so you just put surfactants there on the surface? Or is it actually, it's probably not in the terms of electronic doping, but you have actually...
So yeah, the idea was that we would have the metal in the dot. So that was, what we were trying to achieve. So it did seem to kind of dope electronically to cause the shift. So we did see some longer lifetimes in terms of the emissions. So we guess that that's coming from kind of some dopant state in the dots.
Well, it could be a defect state, right?
Sorry?
It could be a defect state
yes.
generated by the metal.
Yes, that's what.
Because in physical sense, doping, physics actually means you provide free carriers.
Yes.
But that's probably not the case here, or is it?
Probably in this state is probably more accurate.
Do you have any special information whether this dopant actually ends up on the lattice side or the interstitial?
That's a kind of very challenging question to answer, as you can imagine. So I guess the main observation was that if we were doping with manganese and nickel, that essentially they didn't seem to be very stable. So we assumed that probably the manganese and the nickel examples, that the metal is probably sitting somewhere close to the surface of the dots. But the copper one did seem to be more stable, so that one might be more internal in terms of the location of the atom. But yeah, it was more by kind of analogous observations.
Very chemically incorporated.
Yes.
The previous slide you showed the...
Yes, that's right.
Yeah, but I guess some of the TM techniques are capable at least of picking up the position of the atom.
Possibly. I think with some of the EELS techniques,
The operation correct.
We could, if you got lucky, you might be able to hunt it down and find it. Yes.
The other one would be atom protomography.
Absolutely. Yes. So I think that would probably be a better bet actually, and really trying to see some kind of three-dimensional slicing through the dots.
Yes.
To contact the web.
Just a short comment. I think there was actually some aberration-corrected yields work done in Dasbury on manganese-doped silicon for spintronic applications. They were actually able to show manganese atoms on silicon lattice sites, but that was crystalline, single crystalline silicon. And if you got dots, I mean, it's really, you need a lot of TM shots, I guess, to get the right lattice orientation that you really, and you're lucky actually you got a dopant there in the lattice, if it actually makes on the lattice side, because as you may know, the activation energy is quite high.
Yeah.
Yes, thank you for the talk. I've got 2 questions on silicon quantum dot. One question is about the synthesis yield. I'm just wondering, because I know some of the methods for quantum dot synthesis, you get very good quantum dots, however, you get very low yield compared to the amount of precursors that you put in.
Yes.
So I'm just wondering, what about the synthesis yield for silicon quantum dot? Because for making a devices, we usually need a lot of material, to try and make the thin films or whatever. The second thing is, the quantum dots does a good job for emitting light, but it usually does a very bad job for conducting electricity. I'm just wondering, for the surface ligands you have on the silicon quantum dot, have you got, or are you aware of any more conductive ligands if you use the quantum dots to make a film, so it does a better job to conduct electron holes?
So in terms of the yields, I mean, with the solution synthesis, the amounts we make are pretty much milligrams each time, and that's kind of how much we typically make. We can scale up, and we have scaled up, but I guess we haven't had the demand to really develop the scale-ups, so we could possibly do that. There are different methods to make dots with more kind of, say, etching methods, and they can make larger amounts, but they typically have less control in terms of what they're synthesizing. In terms of putting different groups on the surface, we have a good control, or in terms of the chemistry, in terms of what types of molecules we could put on the surface. So if there's any suggestions, then we could very easily or very happily kind of go away and try and put on different conducting molecules onto the surface. So I guess the ones that we've mainly focused on are, so far, have been really looking at groups that will turn the dots water soluble or have water soluble dots, and functional groups which aren't going to be too reactive. So the types of functionalities we've put on have been things like alcohols or amines so far. But yeah, we can easily kind of put on longer or shorter molecules, or molecules which, say, should have some double bonds which might be conducting, for example.
Thanks for a great talk. I was wondering if you've done any shape-controlled nanomaterials in some fancy shapes in semiconductors.
I'm trying to think. We did some work. We made some kind of cubes and hexagonal plates of some cadmium sulfide a while ago. I guess that's the kind of the only system that I remember as kind of making some different shapes. Yeah, but again, if there's something that people would like, we're very happy to have a good crack at it. So Gavin has given us some suggestions for target materials, kind of 3-4 years ago, which we bashed our head trying to make for quite a while. So we're always, yes, that's right. So we're always kind of, if there's any suggestions, we're always kind of open to ideas.
Just a quick question. Ask about your experience for selecting surfactants and like concentration to use, and how will they affect the shape and size according to your experience. Can you make some comments on that, and why you particularly choose TOAV in this case?
So I guess in general what we find, so say in terms of making the different shapes, typically say for this kind of reaction where we're making this cubic shape, in general, there's kind of two regimes where either you have surfactants binding very, very strongly to the surface, and then you can end up making kind of quite faceted particles. So, nickel has a cubic crystal structure, the surfactants bind very strongly, it's keeping to that cubic shape. And actually for the ruthenium shape, it actually stems from the HCP crystal structure. The other type of surfactant system is where you have it more weakly binding, and then you essentially allow the particle to kind of free grow. And that kind of condition is when you can start getting these kind of branch-shaped particles growing. So this kind of system would be where the surfactant isn't binding very strongly, and then the particles just growing very dendritically. I guess what we typically find is that you need to have a ratio of maybe about 10 surfactant molecules for every metal. So it normally is a dynamic system. So you'll have, if you have 10 molecules there, you'll have 10 in your solution and 1 binding to the surface of your particle, but they will be going on and off, and it is an equilibrium. So typically if we have, say, a 1-to-1 ratio of surfactant to metal, you're not getting enough interaction with the surface to really control the growth. So that's typically the regimes we operate in.
Yeah. One more question on the synthesis. You've shown this method where you actually got this flask where you have the precursor solution with the hydrogen atmosphere, and then you use like slow cooking, right? You just heat it up, you got a slow reaction. Though probably with hydrogen it's not quite benign. I guess that's what you meant when you said it's a bit reactive.
It does help, yeah.
If you put a metal in there like nickel or manganese, you actually have like an additional precursor in there, or do you just put a gaseous precursor in?
We put in a solution, so it's a liquid precursor. So it's a bit hard to see in this picture, but essentially you've just got a little solution there. So in that solution there's our solvent, which is dissolving up our organometallic precursor, and then the surfactants in there as well. So sometimes the surfactant can bind to the metal before it's even reacted or reduced, so the surfactant choice can have an effect on that side as well. Yeah.
That's just for metals, it's not for silicon nanophysics.
This is typically for metals. So for the silicon, typically we make the silicon actually in this kind of system these days. Yeah. So the silicon's pretty easy to make. It is all about making sure you get that passivation at the end. Making the dots themselves is not too challenging. It's actually making sure you get that capping right so that they're passivated after the reaction. Yeah.
I just follow up on the question about surfactant use, because most of the work you show here that actually the metal is already in a solid phase, but for the case like you previously described for the silicon tetrachloride, that's in this. I remember correctly, it's actually a liquid.
Yes.
Yeah. So in that case, if you put like 10 times more ratio of surfactant to your material, would you take account into the CMC, the critical shell concentration, when they nucleate from the solution? So do you think this? So what's the consideration you take for how much surfactant you use when you do the silicon chloride?
So again, that was just kind of, I guess, trial and error. We started out just by using quite an excess. The problem with using quite an excess is that you do have to get rid of it at the end of the reaction. So we do tend to use different surfactants. So the TOAB is okay. We use this surfactant as well, which is kind of, the EBID is like a polyethylene glycol unit, and that's actually a liquid, which we do find a bit easier to purify off at the end of the reaction. So yeah, I guess we found that if we use too little. In this reaction, I think the TOAB is quite important. I think that actually binds to the silicon before it reacts. So I think you've got a silicon ion interacting with the TOAB. So I think the TOAB and the surfactant in this particular reaction is actually quite important. I think if you didn't have any surfactant there, essentially you'd just make silane. Yeah.
I noticed that most of the materials that you talk about have been metals.
Yes.
Well, sorry, you actually talking more about silicon metals, but the ones you've actually been making have been metals. Is that because of interest primarily, or are they kind of more?
I guess what we've always largely focused on is doing synthesis for whatever reason in organic solvents, rather than kind of these water hydrothermal syntheses. So I guess there's a lot of groups around the world doing all the hydrothermal stuff, and yeah, you're always looking for a bit of a point of difference, I guess. So yeah, we've always ended up, for some reason, making reactions in organic solvents, and that kind of tends itself particularly away from the oxide materials. So we haven't particularly done much oxide material synthesis, yeah.
And that might also have some bearing on the possibilities of making the binary materials you referred to, the full shell structures, the two metal structures. There must be some limitation on which types of materials you can mix together.
Yeah, that's right. So I guess we've been playing quite a lot with the different growth mechanisms. So, for example, with this system, this is where you have the gold core and the palladium shell. I mean, you have basically an epitaxial relationship, and you can have epitaxial growth to make the shell. And actually, to grow these core shell structures, the slow cooking is kind of essential. So we actually calculated that we were depositing each layer of palladium about one layer every about 14, 15 minutes. So it really is a very slow growth process. So each time the new palladium atom comes down, it has time to really move to the facet and stick on the facet and just keep those facets maintaining. So that's why we ended up still with these kind of faceted particles. And then if you kind of look at this system, this is trying to kind of push it the other way. So rather than having, say, a epitaxial relationship and having a making a core shell structure, we're really trying to push out arms and branches. So this is using with a FCC core and a HCP structure. So that's really going to push to making an arm structure. So yeah, I guess we've been trying to think around different crystal structures and different materials in terms of trying to direct to the shape that we're kind of have in our minds that we're trying to make. Yeah.
Sorry, I just quick question.
Maybe not the last two.
Yeah, just following on the amount of surfactant use as well. Because I saw you using the lithium aluminum hydride to reduce the silicon chloride. In that case, what's your experience on like protecting silicon your surfactant, because like since like lithium aluminum hydride is a strong reducing agent, would you consider the case that some of your surfactant actually will be reacted with the lithium aluminum?
Yeah, certainly the surfactants we choose won't react with lithium aluminium hydride, but sometimes we use a surfactant called ollealamine, which has a carbon double bond in it. And sometimes we do wonder, particularly if we're doing these experiments in the hydrogen atmosphere, whether, for example, you're reducing that double bond. But we haven't particularly noticed too many reactions in terms of the surfactants. Yeah.
Yeah, so you thought you were going to. I never resist asking the plasmonic question. So I mean, how extensively some of these shapes look interesting for kind of potential plasmonic resonances, and certainly bow ties are an interesting structure for nonlinear optics, I guess. Have you looked extensively into any of those?
You know, we when we first made these ruthenium bow ties, and they're all very, very pretty and very cute, and then we were trying to think of some use for them, and we tried to do this galvanic exchange and see if we could, say, for example, keep the shape of the hourglass but exchange it with gold. So I guess what we have done in terms of we've done some experiments, if I can just, so we've done some experiments which I didn't show, but this is having a branch palladium core and then putting gold, decorating gold on the surface. So this is basically for these hypothermia applications. So with the gold present, you can shine on an IR laser, you can heat up the particles, and essentially this again was in collaboration with Taiwanese collaborators, but essentially you shine the laser on the gold coating palladium particles, and then you can heat up the particles and essentially kill and the tumour cells. So in that system we did manage to kind of shift the plasmonic properties, but whether it was the shape or whether it was the interaction between the palladium and the gold, could come from either factor. So it's something we've been toying with.
We've got quite a nice facility for looking at the scattering or absorption, so it might be interesting. If you've still got some materials, I guess it might be a nice thing to look at.
And this is, this one is one we're just writing up at the moment, so it'd be great to chat to you just a second.
Well, we can talk about that later.
No, we can talk about that later. It's a rather specific question.
5 minutes walk that way, so we've got lots of opportunities.
It's not as if Richard's not going to be on that. Okay, well, let's thank Richard again for that. Thank you.